Hello guys and welcome back. Today we start a series of videos for developing STM32 microcontrollers on a very handful IDE, which is the System Workbench IDE. I really replaced Eclipse and its plugins because it really needs a lot of work to get into the programming part. So I'm starting with this IDE. So this tutorial is about controlling the GPIO of the microcontroller, which is STM32 F103 C86, which is called the Bluebell. So let's get into it. Basically, this IDE provides you a very easy way to program and flash and also debugging your programs very easily. Works very well with ST-Link version 2 programmer. So let's start new project. Let's make it C. Okay, so let linking version 1 AC6, yeah, that's it. Okay, so guys, if you open this IDE for the first time, you will not find the board, the STM32 board. So you have to create a new board, new custom board. Enter its name, the series, and select the microcontroller, and that's it. Okay, but I already have done that, so let's proceed. Next, include the standard peripheral library. For the first time it will not be existed, so I downloaded it from here, download target firmware. I can also download the CubeHub, but that's enough. Okay, and yeah, finish. So here we have the system.c file, which really initializes the hardware of the microcontroller inside source. Okay, so why I'm mentioning this, because we're gonna change things here to manipulate the clock frequency of the chip and the linker script and everything. You don't need to do like we've done to Eclipse by adding some plugins and so on. Okay, so the target of this tutorial is to write a LED blinking program like this. This is a pseudocode, and also we will flash it, debug it, and add the semi-hosting feature for easier debugging. Let's get started. Okay, first of all, we need to enable the clock for the GPIO C. The pin that I'm gonna work with is PC13 port C, the 13th bit or pin. Okay, so we need to enable the clock and set the mode, which defines the frequency at which the pin is going to work. The configuration of the GPIO, which defines which configuration should be installed to the pin, push pull or open drain. So, and then the end slope, which is set the pin, delay for some time, reset the pin, and delay for some time. Okay, let's check the required registers from the datasheet of the chip. Alright, open the datasheet, open the RCC registers. Why the RCC? Because the RCC registers controls the clock frequency of all the chip. Alright, so the register that we need is called RCC APB2 enable register, which enables the APB bus, enables the clock to all GPIOs. Yeah, that's it. So in order for us to work and control the GPIOs, we have to enable the clock for each port from this register. So we have to memorize that name, and also it enables clock for many other modules such as the SPI, ADC, and the USART. Okay, port C clock enabled. Okay, so we have to put 1 in the 5th bit. Then we have to modify the mode and the configuration of the GPIO register. So open the GPIO registers. Alright, so GPIO configuration low works with pins from 0 to 7, and the pin that we need is 13, so we need to work with configuration register high. So here is the options. The mode, we have input mode, output mode, maximum speed 10 MHz, 2 MHz, 50 MHz. We're gonna work with 8 MHz clock frequency for the system, so 10 MHz will be okay. So 0 1 to the mode in the configuration register high, and for the configuration bits in output mode we will choose this option, general purpose out push pull. Okay, so 0 0 in configuration bits, 0 1 in mode bits. And then we have to and one thing to note, guys, is these registers that we're going to use to put 1 or 0 to the corresponding bit are not readable. So this register defines and fetches the real values of each pin in each port. Okay, so this is readable, but these are not readable. So the bit set reset register sets the corresponding bit to 1 or 0 in every port, and also resets. Okay, but we're gonna work with the bit reset register for resetting the 13th bit. Okay, so that's what we need to know for now. So let's get into programming. The first thing is, let's copy the pseudocode. Alright, enable the clock for GPIO, which is controlled by the RCC registers, specifically the APB2 enable register. So how we have to modify the 5th bit, as we said, by writing RCC, that's a constant, RCC APB to enable register, GPIO PC input output port C, I guess, enable. Okay, so that puts 1 to the 5th bit in this register. Okay, so let's go to the GPIO C. Register control high, configuration high register, and then we modify the mode bits. GPIO GPIO control configuration high, and then mode, let's see, mode 13. So that puts 1 to the 2 bits of the mode, and that puts 1 to the 0's bit, 1 to the first bit or second bit. Sorry. So that puts 1 to the first bit, puts 1 to the second bit. Okay, we need 0 1, so is that what we need? Yeah, 1 to here we have 21st bit. Okay, so let's see. A 21st bit, 1. Okay, so 0 1, and then for the configuration bits, the same thing. GPIO C, configuration high register, and then we have we need to put 0 0, so 13 and we put AND here, and then we negate these bits, so it's 1 1. Okay, it's 1 1 to the configuration bits. When it's negated, so it's 0 0, and the other bits are 1s. So ending with this does not affect the other bits, but affects the configuration bits. Start and end the slope. Anyhow, so we have to set a PC 13's bit by working with GPIO C, PS or R, and then we modify the 13th bit. GPIO PS or R, and then the PS or, and then the PS 13 bit. Delay for some time. This is a function we will create in a moment, and then GPIO C BRR register or equal to 1 into the BRR 13th bit. Delay for some time. Let's create the function. Which takes a number of iterations. I think that this is it. So the header file, yeah, exactly what we need. Let's build this. Okay, no error. So that seems working. So first of all, we need to flash this into the chip. So I've created a flashing configuration, which has been described in later videos, so you can go back and check them. Yeah, that's the definition of the ST-Link driver. So ST-Flash in this this path, and then we work under the release, and we write the .bin file into the chip. So actually I haven't put it, so let's check it. Alright, yeah, so that seems working. Then yeah, run. Okay, unable to reset target. So one thing to note, guys, is inside the debugger of your program, you will find here an option. You need to change from connect and reset to software system reset. Apply and run. Okay, so verified. Okay, so alright, so let's debug our program, put some breakpoints. Okay, so something we forgot to do is manipulating and changing the frequency of the system. So here we have the definitions for the clock frequency, the system clock frequency. So the default is 72 megahertz if you don't change it. So by commenting this line, the default value is 8 megahertz, which is the high speed internal oscillator, RC oscillator of the chip. So let's build a gain for 8 megahertz, flash it. Okay, so I think we're good to go. So let's debug the program. Alright, and also one thing to note, guys, is here we have the embedded registers available without installing a plugin, so it's easy to work once you have you have installed the program. Okay, so open the RCC, check ABB to enable register, and then already we've got 1 to the 5th bit. Okay, so let's open the GPIO, C, control high, and those are not readable, so we work with the ODR. Okay, CRH has been modified once and then twice, and I think we will see 1 here. Okay, so that's 1 to the 13th bit, and then delay some time, and then 0. Okay, so that's a complete debugging for our program. Alright. Okay. In the next video, guys, to not make this very long video, I'll show you how to enable the semi-hosting feature for printing things you need to know inside your microcontroller. Okay, so until next time, guys, good luck.